By the way, just kind of as a plug, she's got like, this is like, seems like a really interesting talk. She's gonna mix up, some algebra and some geometry, combinatorics, and talk about making time. And she gave us a pretty picture with it. So she's a new faculty, let's welcome her and be there if you can. It should be a fun talk. Okay, so here's kind of where we were. Let me give you the corollary I gave you last time, but it's going to be important in the sequel. This followed from all this business that we were talking about, the equivalent things for R to be Noetherian and zero dimensional. Let R be a domain. Then R is an Noetherian and a dimension less than or equal to 1, if and only if and only if for every non-zero ideal, R mod I as finite. As an R module. So we discussed this a little bit last time. Here's another proposition that we will use. We use this in I think the next proposition 528. And I won't prove this because it's a homework problem. If the dimension of your ring is 0, then any non-unit of R is a 0. And the way I have it stated is in the theorem that any non-zero divisor is a unit, but the equivalent force. This is actually fairly easy to prove if R is a finite ring, just about pigeonholing things. Of course, in general, you can't pigeonhole if R is infinite, but this is a kind of a nice generalization of the finite ring case, and that's a homework exercise. Let me give you the following lemma that we are going to use in our big proof for today. This is kind of I think this one is kind of interesting by itself. If R, or let R, a one-dimensional integral domain, and AS and non-zero elements. And A and C are any two non-zero elements of R, and I guess all we need is we don't need the theory here in the integral domain. If J this is the set of X and R this is the set of X and R that throws some power of A into the ideal generated by C, then the ideal generated by J and A is R. So J is the ideal. It consists of everything in R that throws some power of A into C. Let me prove this lemma. Let me first note that J is not zero. Because certainly C is in there, right? Because C throws over the power of the ideal generated by C, and we assume that C is not zero, so J is a non-zero ideal. So by proposition, five to eight, every how do I couch this here? Every non-zero divisor must be different English there. Maybe that's how it should work. Every non-zero divisor of R mod J is a unit. Let me point out something here. Of course, 528 applies when the dimension of R is zero. So it must be the case, if I'm using this, that R mod J has dimension zero. Why is R mod J of dimension zero? Well, there's a couple of key things here. Number one, R is a domain, and it's one dimensional, right? So what it means that the ideal structure looks like, the prime ideal structure in R is you've got the zero ideal, and then every non-zero prime ideal is maximal, right? So it looks very much like the integers, right? Like that. So when I mod out by a non-zero ideal, there's a one-to-one correspondence between primes of R that contain J and primes of R mod J. But the only primes of R mod J, the only primes of R that contain J are just the maximal primes. And so all primes here are maximal. So R mod J is indeed zero dimensional. So I'm going to abuse the notation here. R mod J. Again, I'm abusing the notation. I really should put a bar over or something like that, because I really mean to coset A plus J here, but I'm going to call it A. And I claim that A is not a zero divisor. I claim that A is actually not a zero divisor in R mod J. And to see this, let's suppose for the sake of argument that A times B equals zero in R mod J. And again, I'm taking B to be an element of R. I'm using the notation I'm using all over the place now. But this would mean that AB AB is in J, right? So what's the deal here? So if you notice that, note oops, so my bad. Since AB is in J, then by definition, there's some power of A that AB throws into C, right? So this is in C for some n in the natural numbers, correct? But this means because look, B satisfies this hypothesis because B throws A to the n plus 1 in the ideal generated by C. And so B is also an element of this, right? So B is in J, and hence A is not a zero value in one like there. That is the closest, it's not. And so that means it's a unit. Because of, again, proposition 528. So J JA is equal to R, right, which is exactly what we want to show. Okay, so I think these are all my ducks in a row. So any questions? Okay, so now let's do the big one. I promised this theorem for a couple of days now. So theorem, if R is one-dimensional on the Noetherian domain and T is an overring, but R be a one-dimensional on the Noetherian domain. And T an overring of R. Then T is also one-dimensional and okay. So let me sort of talk about strategy. Okay, so let's pick a non-zero element, and R. Non-zero is going to be important here in a moment. We wish to show our goal is to show T mod AT is a finitely generated R model. And this is going to do it for us by our collective results here. So why is this going to do it for us? Well, so what I really want to do is I really want to apply this limit here. And I want to apply T, right? Oh, I'm sorry. I want to apply this right here. There we go. I want to apply this to T here. So how do we determine that T is one-dimensional Noetherian, which is our ultimate goal? This theorem tells me that T is Noetherian dimension no more than 1, if and only if for all non-zero ideals I and T, R mod I has finite length. Right? Now, here's the deal. All we need to do is show that this thing is a finitely generated R model. And why is it going to work for us? Well, because we already know that R is one-dimensional in Noetherian, right? So that we know that this applies to R, right? So, so if T is a finitely generated R module, right, then we know that all our finitely generated R modules are of finite length, because this is, since this is finitely generated over R, right, then it's the homomorphic image of a finitely generated free module, right? So, and we know that all those finitely generated modules actually have finite length, so the homomorphic image also has to have finite length as well. And of course, another problem that you might jump out is the fact that this should be T mod I for any ideal. Why is this good enough? But notice that any ideal of T, well, let me strengthen this. No, any non-zero ideal of T contains a non-zero ideal, or a non-zero element of R. Because in fact, T is an overring of R. So if you have any element in this ideal of T, say A over B, where A and B are in R, multiply that by B, and the numerator A is also in this ideal, and there you go. There's your non-zero element in there, right? And it suffices to show this because any T mod I, AT is containing the inside. So this statement really says that if I have an arbitrary element, arbitrary ideal of T, then it contains an ideal of this form, which means that T mod I is a homomorphic image of this. So if this is finitely generated, it's homomorphic image as well. So it's going to suffice to ferret it out for that. And then again, it applies from this right here, because then we'll have that every T mod I has finite, or every module T mod I has finite length. So how do we do this? How do we show it's a finitely generated R module? Well, we were going to define the following ideals. Consider, I'm going to define the following collection of elements here. This is AMT notice that this is these are ideals of A. I'm sorry, R. Right, because this chunk is in R and this is in R. These are ideals of R and forms a descending chain and each IM contains a R, which is not zero. Right? So this is certainly a descending chain, if I agree with that. And every one of these ideals contains AR, that's stable, right? And so this descending chain must stabilize. Why?
It doesn't need to build an increase in chain, right? Well,
the important thing actually here is that they all contain AR and A is not zero, right? Because you can also think of IM this chain corresponds to a descending chain in R mod AR. And this one right here is our attenuant. It's zero dimensional for very much the reason I argued over here. And it's zero dimensional and it's Noetherian because R is, right? So any homomorphic image of the Noetherian ring is Noetherian. So in fact, this thing forms a descending chain. Its corresponding forms a descending chain in R mod AR, which is an Noetherian ring, so it's stabilized. So at some point, this ideal stabilizes. And so, so in particular, I'm going to say that I am equals I n plus k, well, then I numbers. So after I n, it doesn't sink any further, so to speak. Now, at this value of n, I am going to claim that T is contained one over A and R plus A. And the principle is probably just kind of algebra and substitute. I mean, this is an algebra class, and kind of substituting some stuff out. So let's see why this is true. So why does this hold? I'm going to use this in a moment here. Let and here we'll say that B and C are in R. Now select well, notice that this is what we have here. No, A and C are not zero, so we apply whatever limit it was, 529. So we apply limit 529 with A and C just as in the statement of this, and we have the J A is equal to R, where J is again defined as J is the collection of everything that throws some power of A into C. Just as in 29. So let's write one. So let's write one is J plus ZA. Where J is in J and Z is in R. And so we can write T. I'm going to gratuitously multiply this equation by T. All right. So this is PZA. And I'm going to write this more explicitly as B over CJ. Because B and C, B over C is in fact what T is. J times A to the K is in the ideal generated by C for some K. Because that's what it means to live in J. It has to throw some power in there. Notice, let me point out also that if J throws the K power wave and it throws every higher power, it just may not throw in the lower powers. So if you look at Bj over C, this is equal to B over C J AK over AK. Right, nothing up my sleeve, just put those cancelable AKs there. And notice that this bit is in the ideal generated by C. Right, so you can think of those C's canceling. So this is in. So since the C's cancel here, this is actually in 1 over AK times R. Right. And so in this case, so T is in 1 over AK R plus AT. Right, because this thing right here is in 1 over AKR, and of course this is A times something into it. So I've got it taken care of for values of K less than or equal to N. But of course, there's a problem because no problem there if K is less than or equal to N. But what if this power doesn't come online until bigger than N? What if it takes too many powers for A for J to throw it back into C? We're going to show that really can't happen. So if, on the other hand, that's the only thing. If K is too big, then it may not be in that smaller 1 over A to the N R. Assume that K is bigger than N is as small as possible. So basically, as you might expect, what I'm going to do here is I'm going to get a contradiction by showing that K as small as possible. I'm going to show you can do it with one less with K minus 1 and contradict the minimality here. So in this case, what we have is T is U over AK plus AT1. So where, of course, in this case, U is an R. So U is an R and T1 is an T. And K is as small as possible. So what can we get from that? Manipulating this equation, I get U equals A to the K T1 or T minus AT1. And so U this is in A to the KT because that's certainly something in T. And it's also in R, because U was supposed to be in R in the first place. But since K is bigger than N, right? Remember, N was the crucial point where that descending chain stabilized. So since K was bigger than N, then IK because N is the point of stability, so everything beyond that is all the same ideal. So U is equal to A to the K plus 1, T2, plus AU1. Right, because it's also the K plus 1 ideal. So substituting we obtain, so use these two equations here, and what I get is U1 over A to the K minus 1 plus A T1 plus T2, that's right, is equal to T. This is in R times AT, but now this contradicts the minimality. So what do we have here? We have our containment. T is contained. 1 over 8 N R, let's say, which is what we claimed here. So it is contained. And a cyclic. R module. This modeling out by AT here, and so is fine. And that's all we needed to do to show what we needed. It's really interesting because there's just a couple of points. There's just a couple of obvious points where the theory of one dimensional come up, mostly in the limits that build up to this. But this is very important because if you start picking off those adjectives, one dimensional Noetherian, you start running into trouble. Okay. Any questions? Okay. So, whatever this is, there's actually one more theorem. It's a total non sequitur that I'm going to move up here. We're on Dedekind domains. How many of you have heard of class groups? Right, in your travels. So where do you see them, like number theory, things like this before, right? So we're gonna take this apart, and I'm gonna do some things, especially that relate to algebraic number theory, do some computations. But first, let me give you a theorem. And this is before Dedekind, and I've done some examples of this, although I haven't really defined it. So let me define something This is a class of domain that is between proofer and Dedekind. Theory. Let D be a domain that is not a field. Not a field. The following conditions are equivalent. One, D is almost everything. Maybe I did define that earlier. Well, I'll see something about it. Actually. The cancellation, holds for non-zero ideals D. Non-zero ideals D. So let me explain what that means. You have this equation, I, A, and B are all ideals of D. If I equals IB, then A equals B. Actually, usually speaking, you can't cancel ideals like this, right? Matter of fact. Two, it's actually pretty rare for cancellation to hold. D is one-dimensional proofer domain with no item code maximum ideal. D is one-dimensional proofer and no maximal ideal is item code. And there's what I need out of field. I is item code. You know, I squared is equal to I. To be for an ideal to be item code, it has to be sort of not finitely generated in the extreme. Just not finitely generated is not going to do it. So these are one-dimensional proofer domains where so that is when you take the maximal ideal and you square it, it actually gets smaller. Right, it gets strictly smaller. 3, D is a proofer domain, and the intersection of all powers of ideals are 0. For all non-zero ideals, A and R, and I want this to be actually, I want to make proper. The intersection is so a domain that, not a field that satisfies all of these is called, an almost every domain. One, hence all of these conditions be called almost every. So. So you've got your proof domains, which of course, I can't resist this. Valuation domains. And of course, there's a class of domains that contain valuation domains, but I don't want to drive and get too far afield. And inside the proofer domains, you have almost Dedekind. And this is sort of a much smaller class because proofer domains exist in all dimensions. Almost Dedekind domains actually have to be one-dimensional, as you can see from this. And among the almost Dedekind domains, right, feels right. It's precious. Lost my mind. Okay. So the strictest type of the strictest condition is yeah, these are independent. So you have every let me draw this again. Let me get it this way. Which implies, and of course, any proof of domain is almost anything. I'm sorry. Right, any valuation domain is proof of domain. Any proof of domain. Yeah, so we've got it going this way. This is what my problem is. Certainly, any valuation domain is proof of domains, and any almost Dedekind domain. Proof, there we go. That's what turned me off. And of course, any Dedekind domain. Or any Dedekind is almost Dedekind. But of course, Dedekind domains aren't necessarily valuation domains, right? Because Dedekind domains don't have to have linear order ideals. Valuation domains don't have to have all non-zero ideals vertical, right? So, but anything that's Dedekind is almost Dedekind. Any almost Dedekind is proofer. Evaluation is proofer. And of course, Dedekind domains and almost Dedekind domains are of course infinitely close. They're intersections of these evaluation. It's there. Chart a little bit better there. And it's interesting because at this level, at the Dedekind domain level, what you have is that every non-zero ideal, every non-zero proper ideal can be factored into primes. Here, not necessarily, but you do have and at the proof of domain level, you don't necessarily even have cancellation of ideals. But what you do have is you do have that every finitely generated ideal is invertible, or maybe what's better for proof of domains is its local evaluation domain. Right. So if you localize at any prime ideal, it's evaluation domain. let me, give you a first, so we're gonna go to Dedekind domains, which are, we're gonna focus on that for a little bit. I think the theorem, well, or the point of what I was trying to say here is that what I was trying to say here is that, Dedekind domains are, in a certain sense, sort of farther away from being a proof domain. They're sort of closer to being Dedekind. Well, you can probably homework. Who's snarky? So, the Dedekind domains, almost Dedekind domains can be very, very, very strange. Almost Dedekind also means, I should put in four. Well, D is almost Dedekind. If, well, let's say DM is a Noetherian valuation. For all, in my spec. Now let me make a couple points. Now I'll bring this one up. That's the one that I wanted to connect with. I'll bring this one up because one of the conditions for Dedekind, one of the equivalent conditions for Dedekind is this. R is Dedekind, R is Noetherian, and then that condition. All right. So the only difference between this condition is the adding of the hypothesis to the theory, right? But we've seen an example where D localized at M is Noetherian for every maximal ideal, but it's not Noetherian, that kind of crazy thing, crazy ideal thing. And so weird things can happen too. By the way, let me point out that what I wrote up there also implies, even though I didn't say it here, this also implies that D is one-dimensional, right? And the reason is because suppose that D is a dimension bigger than one, so you have this. Then if you localize at DM, then you actually have a two-dimensional valuation domain, right? And two-dimensional, assuming it's valuation domain, no valuation domain of dimension bigger than one is ever Noetherian. So you might think about why that's true. If you have any valuation domain whose dimension is bigger than one, it's never Noetherian. And let me also give you a word of caution: just because it's one-dimensional doesn't make it necessarily Noetherian. Okay, we'll start off with theorems of Dedekind next time. Any questions? Any questions? Okay, seriously, think about coming to the math club today. If you got a chance to do that, stay dry and have a good weekend.